Yeah? All right, so this is the art of packet analysis. Why is it called the art of packet analysis? Because this field, to this day, with all the expert engines, even in Wireshark and any other tool, including my own company, Riverbed Products, there's still a lot of art involved than science. And you'll see why that's the case. So this is why I call it art of packet analysis. That's my information on the screen. I do have 25 years of troubleshooting, hardcore troubleshooting, packet analysis, in some of the largest companies in the world. So the company that I used to run around in 2 years ago now, almost 2 years ago, has 300,000 users, 105 country presence, tens of thousands of routers, right? 20, 30,000 routers and switches in the node. So that's kind of the network that I'm used to troubleshooting in. And that's also, I also started from university background as well. So this is my experience, hardcore routing and switching, in addition to packet analysis. Okay, so that's the profile. There's one thing that I want you to remember, and that's box.com/Sharkfest 2014. Not too difficult. Why? Because the PowerPoint presentations, the packet analysis, trace files, and this recording, this Camtasia recording, will be uploaded to box.com/Sharkfest 2014. Okay? One of the things that we do at Sharkfest is we convert these to PDFs. And of course, if you convert, with animations and layers of PowerPoint into PDF, you get a jumbled PDF. So sometimes the actual native PDF, PowerPoint is better. So if you need it, just grab it from box.com/Sharkfest 2014. If you're curious, yes, Sharkfest 2013 will get you to the content from last year. So not that difficult. Okay, okay, that's it. And then this morning, talk about a kick in the pants, I found out something. So just before the keynote speech, a colleague of mine, Chris, who's doing the REST API programming session later today, said, oh, you know what, my epoch time, my birthday and epoch time is a pretty simple number. I said, oh, really? Put mine in there. Let's see what happens. So this is what it came up. And I said, 12283, you can see right here, 122830780. That's my epoch time, or I'm sorry, the in seconds is 122283078. And I said, well, that's not too bad. 1222, kind of 83078, kind of easy to remember. And those of you that don't know, everything in computer science is really measured from epoch time, which is January 1st, 1970. And then Chris notes, oh, but look, you got a minus. I said, I thought that was a dash, and I thought, well, yeah, of course. I was born before epoch time, so you have to go backwards. So the kick in the ass part is I'm older than beginning of time. So that's a nice way to wake up and say, holy crap, I'm older than the beginning of time as far as computers are concerned. So that was kind of a nice, anyway, so let's get started. Oh, and then finally, every time I come to Sharkfest, you saw that I started from 2008, the very beginning one, and this is a passion of mine, and I hope it comes through. And I say this all the time, that it is, in fact, a passion of mine. And everybody asked me for the last 7 years, hey, are you ever going to write a book? And I said, maybe. And in fact, back in the Usenet days, I've said this before too, an editor from Addison Wesley, textbook publisher, contacted me over the internet, said, hey, we think you can write a book. Have you ever thought about it? And I said, no, I'm studying for this, I'm studying for that. Got a baby coming, so I postponed it. And then this year, I finally got off my lazy ass and decided to write one. So I'm on my way. I expect it to be done. I was supposed to be done before the Sharkfest, but life happened. And so hopefully by Q4, that's my goal now. That's my next new goal. So the one thing that I need help with is motivation. Right after Sharkfest, I'm very motivated, so I'll probably end up knocking out like 2 chapters. That's my goal. But if you guys constantly ping me like, hey, is that done? Is that done? Is that done? That'll help me, prod me along as well. Okay, so let's talk about TCP. I always say this not in a pejorative way, not in a bad way, but most people that I find who say they know TCP don't really know TCP. Okay? And the goal of my sessions at Sharkfest, especially the advanced session, is for you to truly understand TCP, not only academically, not from an RFC textbook perspective, but from a troubleshooter's perspective. There's two different ways to analyze TCP. One, purely academic sense. And Dr. Cerf talked about some of the research that's going on, congestion control, etc. But beyond that, so that's all fantastic and that's great, and you got big brains and people doing that stuff. That's great. But as a troubleshooter, sometimes we need to understand practically what's happening and why the network is behaving, why the packets are behaving, why the applications are slow, etc. Okay, so that's kind of my goal of what I want to accomplish today. So, I'm not going to. It's a kind of a large audience, large hall room, I should say. Hard to do Q&A, but when we talk about TCP, these are four things that almost always come up. Why? Because that's drilled into you from books like Comer and Stevens and the RFC. Okay, and it's reliable, but. And I felt I'm guilty of this too, and I parrot this, right? Oh, TCP is reliable. There's poor redheaded stepchild UDP, unreliable. So why is TCP reliable? So if you stop and think about that, well, why is it reliable? Does it have a courier with each packet that ensures, is there a packet angel that ensures that it gets delivered on time? No, it's not, right? So why is it reliable? And the answer is simple. So I'll also say that I took some artistic license with some of these definitions because I don't want to get into the weeds. So some of you may say, hey, that's not 100% accurate, but at this, considering this is a basic track, it's good enough. Okay, so that's where the artistic license comes in. But anyway, having said that, it's reliable because what TCP does, it copies data, it Xeroxes data before transmitting. Because TCP does not have the luxury of asking the Word document or PowerPoint or spreadsheet, hey, you know what, I'm sorry, you wanted that saved? What can I do? I lost a packet, right? The network got dropped somewhere, I don't have it. Could you give me a copy of that spreadsheet one more time? That's not going to happen. So what TCP does, it has a buffer that stores the data before it gets transmitted. So if it gets feedback, and we'll see this in a second here, when TCP understands that there was packet loss, there's data loss, whatever reason, it can go back into its storage and make another Xerox copy and retransmit. Okay? So you have to understand that the retransmit mechanism does not have any OS or application dependency. It's purely a function of TCP. Connection-oriented, very polite protocol. Why? Because unlike UDP, TCP goes knocking on the door, that's the SYN, and then the other guy comes knocking back on your door to say, yeah, I'll talk to you. That's the SYN-ACK. It turns out, from a troubleshooter's perspective, SYN-ACK is very valuable. Not just because it has information that's only in the SYN-ACK, which we'll see later, but also because it's a good source of measurement about latency. It's also the perfect place to find out if you're closer to the transmitter, or if you're closer to the receiver as far as a packet capture point is concerned. Okay? As you get more and more advanced in your packet analysis, the picture, the symptoms will change depending on whether you're closer to the sender or if you're closer to the receiver. And you need to understand that there is a difference. Okay? And we'll see that in a second. By the way, can you hear me okay in the back? I feel like, okay. So I didn't know if that was a thumbs up or the volume should go up. So thank you. All right, so connection or flow control. This is where I say it's end-to-end flow control, and this is a built-in traffic report. Think of it that way. Google does a great job, for those of you that use Google Maps, about giving you a traffic report, and it's scarily accurate. What TCP does, something similar. And it was interesting that Dr. Cerf talked about that infinite buffer because I've seen that in real life as well. Right? And the answer isn't always to increase the output queue on a serial interface. In fact, it can fool TCP into thinking there's more bandwidth than there is. So when you have buffers, and the whole job is to buffer that data, and it's basically tricking TCP, then that's not a good thing. Because TCP has built-in traffic report to throttle down and throttle up. And in some of the later advanced sessions, I may go into that in detail as well. Okay? That in and of itself can be a 1-hour topic. Number 4 is something that you guys need to understand as a troubleshooter. Packets. We call this packet analysis, but TCP has no concept of a packet. Okay? And someone asked me this recently. What happens on a long-lived TCP connection? When does it end? Or someone said, I'm expecting a packet to show up, but it doesn't show up. Who's at fault? Okay, let me give you a context of what that question was about. This person had a working example where they got 3 or 4 full-size packets and a small size with a push bit signifying the end of that buffer. On the non-working trace, there's 2 full-size packets and nothing else. So keep in mind, they're doing an A and B comparison test. Working, non-working. The working version has 4 or 5 packets with the push bit at the end saying, and I'll show you what that means in a second. And the non-working version has 2 packets, but nothing more. But the communication stops. And the question that was asked was, who's at fault? And I said, you'll never know. You'll never know because TCP has no beginning and no end, except for the SYN, ACK, and FIN. Okay? Except for the connection setup, connection teardown, TCP world, there is no beginning and end. Until someone resets the connection, until someone sends a FIN ACK to say, I'm done with this session, the application can nail that connection up for days. And the only thing that's required periodically is a heartbeat to say, I'm still here. Okay? So that the garbage collection and firewalls won't knock it off prematurely. The point of this whole story is that TCP doesn't care about packets. That's the job of Ethernet and IP. And TCP's job is to get data, octet, from one location to the other. And in fact, you'll see as you get more advanced, when you're troubleshooting retransmissions, sometimes some TCP stacks will even packetize smaller packets that were sent. So imagine this. 3 packets of 500 bytes were sent in 3 separate packets for whatever reason. Doesn't matter. All 3 of those get lost. Some stacks will retransmit 3 packets, 500 bytes at a time. Some stack will send 1 packet, 1,500 bytes. Okay? Now, those of you who are more advanced will say, that can't be possible because that's the MTU and MSS is 1460, but I'm making the math easy. Okay? So in other words, what I'm saying is, even some stacks, when it retransmits, it will say, oh, wait a minute, you lost these contiguous frames, this amount of data, 500, 500, 500. I'm not going to individually retransmit them. I'll just put it into one packet, one stream, and send it out. Okay? So again, very important that you understand it's stream-oriented. Sequence numbers. And you like that animation? Pretty cool, right? Ethernet IP TCP. I paid $70 for that animation right there. So I hope you enjoy it. And we're going to sit here and watch it for a little bit, get my money's worth. So sequence number is the most fundamental thing to TCP analysis. It's so important that if you cannot do sequence number analysis, you need to go put in a job application at McDonald's and flip burgers. Because you will have no chance of advancing in this field if you cannot do sequence number analysis. That's how important it is, and we'll go through that today. Okay? So, if you get nothing out of this session today, 2 things. Box.com/Sharkfest 2014 for the content. Number 2, sequence number analysis. And then we're going to hit a corner case. I debated what to hit for this basic topic. And the one that I chose was Nagle, Delayed-Ack, Deadlock, that happens. So I'm going to go through that presentation quickly, and then we'll hit the actual Wireshark. Okay, so bear with me. What is Nagle and delayed acknowledgement? This is a corner case. How many of you, show of hands, work for a financial company? Some kind of financial. Okay, all right. So for those of you in any kind of online transaction or financials, especially investment banking side of the house, this is something that you need to pay attention to because your applications may be paying an inordinate amount of penalty because of what Nagle intended to do and delayed acknowledgement intended to do. Okay? So what is Nagle and delayed acknowledgement? Let's talk about that. Essentially, Nagle's motivation, okay, what he wanted to do was, you know what, it's silly to send a packet for every character, for example. Why don't we wait a little bit to see if we can fill up the MTU, fill up the cargo before we actually transmit. The idea here is you don't want a bunch of metro buses, muni buses, or whatever your bus system is considered, carrying 1 or 2 passengers. Okay? Sit tight, wait at the station, and let the passengers get on, and give them some time so that you can maximize cargo space from a packet standpoint. Okay? Delayed acknowledgement is similar. It's intended to prevent something like, hey, you know what, my window size just increased by 2 bytes. You know what, my window size, my receive window size, we'll talk about that in a second, my receive window size increased by 5 bytes. Okay? So if you wait a little bit, chances are you can do a couple different things. Number one, you're not wasting bandwidth letting the other guy know you got the packet or the data. Okay? Because the acknowledgement is, hey, I received those data bytes. We're good to go. That's ultimately what acknowledgements do. And delayed acknowledgement ensures that you have a chance to get more data so that you can collectively say, yep, I'm good up to data bytes from here to there. Which is all fine and dandy, and rewind when Nagle and delayed acknowledgements were being talked about. Network bandwidth was at very much a premium, and that's why all these technologies came about. But if you put the two together, bad things will always happen. So there are not too many times where in this field there are absolutes. If you have transaction, online transaction type behavior, tiny packets, and you have Nagle and delayed acknowledgements on, which a lot of times it's the default, you will have this deadlock. It's guaranteed. It's a mathematical certainty. So let's see the other aspect of Nagle, and then we'll get into some of the more animation and then the actual packet analysis part. The Nagle rule is pretty simple. And the Nagle rule says, excuse me, I'll edit that out later, so don't worry. The Nagle rule says, if there's unacknowledged data, don't transmit. Meaning this. I sent some data to the other side. He hasn't acknowledged it yet. Excuse me. Okay? So I sent 100 bytes. He hasn't acknowledged me. I have some more data. I can't send it because I need to know he's caught up, essentially. Okay? And that's if it's less than the full size. If it's a full MSS, you can transmit. So that's kind of where Nagle comes in. In other words, sit tight at the bus station. Don't leave the bus station until passengers fill up your bus. That's the analogy that you want to think about. So when can you go? Well, if the bus is full, you got to go. Okay? And so same thing happens in Nagle. If you reached full MSS, maximum segment size, that's the maximum segment size is how much TCP length can fit into a Ethernet IP packet, you can go. The other part is if everything's been acknowledged, and I have a tiny amount of data with the push bit set, then I can go. We'll see this in action, so this is just setting this stage. And then the other part is you can't wait forever, so there's yet another timer that goes off, and then you can go. Because obviously you don't want to come to a complete deadlock, so there are built-in timers to trigger this. Okay? All of this is in RFC 896 and 1122. It's also in Comer and Stevens, and these are words that you can Google and look for because if you don't read in this field, again, it's very difficult to succeed. There are only so many Sharkfest sessions, and so you really have to have a deep understanding. So let me give you an example of troubleshooting Delayed-Ack Nagle so we can watch it visually, and then we'll get to the packets and figure out what's happening from a network perspective. Okay, so the first rule, wait for the bus to be filled. Once that bus is full, take off, which is exactly what's happening here. Okay? And then you'll notice that acknowledgement came not immediately, not after this first data was sent. Okay, so this bus is full, you saw the animation, Bus is full, data can go, right? That's the rule. Bus is full, you can go. Over here, bus is full, you can go. But in my diagram, my animation here, which I spent considerable amount of time for your pleasure, the acknowledgement came after the second one. Why is that? Well, that's where the delayed acknowledgement kicks in too. The rule of delayed acknowledgement, there's two different rules. Number one is, let's look at how Microsoft handles it. And so let me show it to you with this one. So here's sense and ack, and let's find two instances, maybe this guy here. Two instances, sense sent, and then we have an acknowledgement that come back. Okay. There's a delay here. What's going on there? We'll see why that's the case. Here's data packet from 190 to 168. Is that visible? Should I make the font size a little bigger? Yeah? A little bigger? Okay. Oops. All right, sorry. Let me adjust my OCD is kicking in, so I have to get the columns to the way I like it. All right. So here's a packet. There's no length, so keep in mind there's no length here. So this is not a TCP data. This is just a pure acknowledgement. Here we have data, and then we have acknowledgement. Okay, so let's follow this particular example. So I have 124 bytes. Everything's caught up. It has a push bit. So that rule has been met. Okay, everything's been caught up. There are no outstanding bytes on the wire. I've sent you everything I needed to send to you. You've acknowledged that you received everything that I sent to you. So the rule is, if you're all caught up and you have a tiny packet, but you also set the push bit, you can go. Okay. Then he can go as well. Now some of you should be thinking, well, wait a minute. How did he go? How could he go if there are still bytes outstanding on the wire? Okay. For those of you that don't know what I'm talking about, it's okay. We'll get to that in a second. And then, of course, here we have an acknowledgement that come back. Okay, 172.16, 1.1 comes back. Okay. So let's go back to the beginning. And let's look at the sense and act first and try to identify, am I closer to 192.168? Am I closer to 172.16? It's important. So sense and act. Knocking on the door, he knocks back at your door, and then you say, okay, I heard your knock. That's what TCP does. Knock on the door, he knocks back, you acknowledge that he knocked. Connection oriented. Okay? Very polite protocol. So, looking at this, imagine this is the dawn of time. This is the beginning of time. We have no idea, looking at this trace file at this point in time, if we're closer to 192 or 172.16. Okay? But there's a hint here. So imagine you have to be the packet, you have to be the network, you have to be the sniffer on the network. So mentally draw this picture in your head. At some moment in time, you see a SYN packet go across. That's the only data source you have. A SYN packet went by at some point in time. Okay? And then 128 microseconds later, you see a SYN-ACK. Okay? So imagine packet zooms by. You don't know where you are in terms of proximity, 192 or 172, closer to one or the other. But then you notice that 172.16 guy, in packet number 8 here, he immediately acknowledges, and it took him about 128 microseconds. Okay, so let me repaint the picture. You see a SYN go by, and then in 100 microseconds, a SYN-ACK comes back in the other direction. Okay. And then finally, we also know that the other guy has to say, okay, I acknowledge you. And that took 300 milliseconds. Okay. So Am I closer to 172? Am I closer to 192, 168 guy? 172. Because in packet number 7 here, beginning of time, I don't know whether I'm closer to the left side, to the right side. But the second packet gives me a clue. The second packet, I must be closer to him because I got that packet within 100 microseconds. And then the final part of that conversation, which is the ACK, took 300 milliseconds. Okay? So if you draw that on paper, you'll see that, in fact, you are closer to 172.16 perspective. Okay. All right, so let me go back to, I kind of put some Easter eggs in when I talked about, hey, how come he sent when there were outstanding bytes on the wire? Remember I said that? Let's go back to our presentation, finish up Nagle, and go back to troubleshooting. Okay, so this was the first example where 2 full-size packets went. This is a very simple case. Very classic case when bulk transfer like FTP or downloading large web objects are involved. This one is a little bit more nuanced because we have a data that's sent. Okay. Data is sent. So we have unacknowledged data on the wire. Notice there's no ACK yet. Okay, so we send some data, and then we have a case where data is being accumulated. So Nagle kicks in because I have unacknowledged data on the wire. What's an unacknowledged data? I sent these 2 packets worth of data and I haven't gotten an acknowledgement yet. I don't know if they were delivered yet or not because an acknowledgement didn't come back. So Nagle kicks in and I have to sit here and I have to buffer this data. The entire block of the yellow here is the full MSS. That's what that's signifying. So I'm accumulating, and I notice that I get a push bit, okay, which is great. The application is saying, hey, I'm done. I flushed the buffer. It's up to you now to deliver this packet for me. Okay, so from an application perspective, he did what's called flushing the buffer. The problem is, I cannot transmit until this acknowledgement comes in. Why? Because there were unacknowledged data on the wire. So as soon as this acknowledgement comes in, even though this is not a full size, because he acknowledged everything that I sent to him up to this point, and because there's a push bit set, I'm free to transmit. Okay? Make sense? Now, had this packet here being transferred is full size, had it filled up the entire MSS, he can go too. All right. Now let's take a look at this example. I sent some data, and a non-full MSS packet's being buffered, and there's a push bit set. Okay? So we have full-size data that went out, no ACK yet. I'm waiting because Nagle kicks in. Okay? But the application is done. He doesn't have anything more to send, so a timer expires, and I can go. Okay, so let me go back in animation here. I sent some data. Some amount of data came with a push bit set, but I can't send it right now because I haven't heard an acknowledgement. But I can't wait forever, so once the timer expires, he can go as well. Okay. And you don't often see this for a couple of different reasons, which I'm not going to get into for now, but this is something that you should keep in the back of your mind. Okay? Again, the analogy is you're a bus driver, you can't wait forever, you have to go at some point. Okay? So there's an override timer built into it. If this were an advanced session, I can go into why you typically don't see this. Yes, question. Okay, so back at the microphone. The question was, because we don't understand about the deadlock, he can't go. What happens if the application has more additional data that it needs to transmit, right? And what happens to that? So the artistic license will kick in here and say that there's a send buffer and additional buffers in play that allow the so it's not like as if the application can't do anything at all. Okay, so you'll see typically what happens is you'll see transmissions where you have chunks of data bounded by push bits. Okay, so chunk of data push, chunk of data push, chunk of data push. Think of the push bit as the last passenger getting on the bus. Sometimes it's full, sometimes it's not, with a push bit stamped on his head saying, hey, the application is done writing, if you're ready to go, we can go. Don't expect anybody to come behind me. Okay? But there are other buffers in play. All right? And we're going to see that in the advanced session as well. Okay. Yes, question. Okay, so the question was the Nagle timeout delay. I put 200 milliseconds. RFCs typically give you guidelines. Delayed acknowledgement says, hey, make it about 200 milliseconds, but don't exceed 500 milliseconds. So a lot of the stacks take those guidelines, but they are completely dependent on the operating system and the stack implementation. Okay. I said that, okay, we've seen Nagle. Now let's see the Nagle Delayed-Ack deadlock. This is where it's very easy to spot, number one. Okay, number two, it's a horrendous penalty to an online transaction, especially if you're financial, because TCP is wasting vast amounts of time because of these two rules. Let's see it in action. The first rule, we sent the data. Okay. So let's read those two bubbles in the case. I sent it 1 packet's worth of data, full size or otherwise, it doesn't matter for now. The problem is, that's all I got to send, 1 packet's worth of data. Okay? So you'll see here that that's what this black represents. He sent the data, but there's nothing more to send. Okay? I can't send anymore until I get an acknowledgement. In the financial world, this is, hey, I want to make this trade. Please let me know if you're going to accept it or not. I can't give you another trade until you confirm my first order. Think of it that way. Okay? The problem is the receiver, he's waiting for another packet before he acknowledges that. Because the rule says, accept 2 packets before you acknowledge. That's the Delayed-Ack rule. Okay? In Microsoft world, any 2 packets will do. If you receive 2 packets back to back, you immediately acknowledge that. In Unix world or Linux world, most often it's 2 full MSS packets, so 2 full-size packets, and you can immediately acknowledge. That's the rule. 2 packets, immediately acknowledge. In Microsoft, any 2 packets will do. In Linux or Unix world, 2 full MSS size packets, you can immediately acknowledge. Now we have a deadlock. Why? I only have 1 packet's worth of data to send to you. But you're not going to acknowledge me because you want 2 packets. So we sit here, I'm not transmitting because I can't, and you're not giving me an acknowledgement because you're waiting for another packet. This is the deadlock. Okay? Then the receiver finally gets tired of waiting, and there's a Delayed-Ack timer, typically 200 milliseconds. Sometimes it's 50 milliseconds. Sometimes it's 100 milliseconds. As you get more advanced in your packet analysis skill set, you can start to build a mental map of how different OSs differ in terms of timer. Okay? A lot of Solaris boxes were tuned down to 50 milliseconds, for example, for Delayed-Ack. The most common one is 200 milliseconds. So 200 milliseconds later, and again, I'm waiting and waiting and waiting. The acknowledgement is not coming because he's waiting. The receiver is waiting for 200 milliseconds to acknowledge that. Okay, but why 200 milliseconds? Because he's waiting for another packet to show up or a timer to go off. In this case, I only have 1 packet's worth of data to send, so he can wait. I'm not going to send him anymore. So the timer expires, and when the timer expires and the acknowledgement comes in, I can then send the next packet. Does that make sense? So this is the deadlock that occurs again and again and again. Let me rephrase it and paint the picture for you one more time. I send you 1 packet's worth of data. I don't have any more. And I can't send you anything else until you acknowledge that 1 packet that I sent to you. You as the receiver are not going to acknowledge me because the rule says acknowledge every other packet. Acknowledge every 2 packets. But since I only sent you one, you're not going to acknowledge me. And you wait, and you wait, and you wait. You get tired of waiting, and then finally, after the Delayed-Ack timer goes off, you send me an acknowledgement, which then frees me up to send my next packet. And this cycle repeats itself ad nauseum. And why did I say like online transaction? Because if you're doing FTP or bulk transfer, you have nothing but full-size packets going out, which means the acknowledgments will come rapid fire. Okay, so when you're doing bulk transfer, this never happens. Yes, question in the back. All right, so let me go back to my podium so I can do the recording and repeat that question. So I just got done saying that in bulk transfer, this never happens. Again, my artistic license kicked in, and the question was, or the comment was, hey, even in a bulk transfer, at the end of that transfer size, you're going to have a small packet. And so the answer is absolutely. However, being that this is a basic session, we're going to kind of skip over that. Okay, and if we have time, we'll come back and. One second. But the net of that comment is that no one can create an application that fits into perfect packet sizes, and when he's ready to flush the buffer, it fits into that packet perfectly, 1460 bytes every single time. So at the very end, you have a little leftover that's small in size. Okay, does that make sense? So let me give you one more analogy, and again, I'm bordering on going off the reservation into a more advanced topic. And Jasper's like, yeah, you are. But I'll give you one final analogy, and it'll help you understand this. You have a bucket of water that you need to transfer. This is what the application is giving you. You're the TCP. You have a ladle, and you're spooning out that water from the bucket. And it's perfect because you have a full ladle size that you're dumping out of that bucket. When you get to that very bottom of that bucket, you don't have a full ladle worth of water. So what happens? You have a half a ladle, half a spoon's worth of data. You still have to let it go. Okay? So typically in the bulk transfers, the very end of that bucket size, you'll have a little bit of data with a small packet. Question? Remember so the question was, hey, the sender has a timer as well, so wouldn't that fire? So when I talked about that corner case when Nagle timer expires, I made a comment, kind of, fleeting comment. You almost never see this. The reason is because the Delayed-Ack timer typically kicks in first, which allows the Nagle timer to say, never mind, because I got the acknowledgement that I needed. Okay? So, but again, I'll just bring out this topic. This is a very advanced scenario, but this in itself is a raceway condition. Okay? There's a Delayed-Ack timer that's going off, and there's a Nagle timeout that's going off as well. And this is another reason why, depending on where you are, you'll see the one timer effect versus the other. Okay? So I'm not going to elaborate on that because I'm getting into the advanced topic, which I said I'm not going to do. All right, so the bottom line is this. Let me recap, and we'll look at it from a packet level example and put it all together about what we learned. I sent a packet here. That's all I have to send. I have nothing more to send right now. Problem is, I can't send anymore because the next packet isn't full size, and it's tiny, and it's got the push bit, but I have unacknowledged data. The guy, the receiver, doesn't acknowledge me because he's waiting for another packet. Okay? 2 packets is an acknowledgement. If it's not 2, you wait. So the 200 millisecond delay kicks in, finally sends an acknowledgement, which then allows me to send this data out. Okay? Make sense? Sort of, kinda? All right. Now, we're going to see it in the packet, and everything I have said seems like will be a lie. And let's find out why that's the case. So here's our example. Since and ACK. That's perfect. Okay? What are some of the things that we need to be aware of? What are some of the things that we want to look for? Push bit certainly is important because push bit allows Nagle to say, okay, I'm at the end of the buffer, I'll wait. So push bit gets preferential treatment, right? So let's look at it from this example. 192.168 has 124 bytes of data to send. Okay. And then immediately we see another packet show up. And we've already established that we're closer to 172.16, right? Correct? So once we set up the connection, all of a sudden I see that the guy has sent me a packet, 124 bytes in length. You can see the length is 178 here, 124 down here, because this has Ethernet IP overhead, and this is the pure TCP size. Okay, either way, it's a small packet, and then he immediately sent me another small packet. What's that about? Didn't we just break the first rule of Nagle? You sent a small packet. You sent me a small packet, and then you immediately followed up with yet another small packet. Why is that? We just talked about this, right? You send a small packet, what do you have to do? You have to wait until you get an acknowledgement before you can send again. So why is it in this case, I have back-to-back small packets coming in? Why is that?
So the receiver doesn't have to wait.
Because
So the receiver doesn't have to wait for 200 milliseconds.
so the receiver doesn't have to wait, but we're not going to talk about the receiver yet. We're going to talk about the sender's perspective first. Why is it that this sender, 192.168, can send back-to-back small packets? What's the simplest answer? Nagle's disabled. Okay. He disabled Nagle so that he can do exactly what Nagle doesn't want you to do: send tiny packets back to back. Okay, make sense? But there's a little bit. So if that were the case, class is over. It's uninteresting. Okay, so we're going to continue on. So here we see that within a millisecond or so, we acknowledge, and let's take a look at the acknowledgement number. Okay, acknowledgement number is 290, and over here you see that next expected sequence number is 290, and here we acknowledge 290. Okay, you can see acknowledgement number here. So 172.16 immediately says, you know what, I got two small packets, I acknowledged you. What operating system is 172.16 running? Microsoft. How do I know that? Because if it were a Unix box or Linux box, he will want two full MSS packets before acknowledging. Okay, so I can make a, not 100%, not a guarantee, but I can reasonably conclude that this guy is running Windows operating system. So now let's look at 172.16's perspective. He sends 16 bytes of data. He sends 38 bytes worth of data. And then 192.168.1.1 sends an acknowledgement of 55 bytes. I'm sorry, acknowledgement number of 55. So let's look at this example. 172.16, sequence number 1 through 17. Okay, byte number 1, add 16 more bytes. Next expected is 17. We come over here. We go to 17 to 38. And then the next expected sequence number is 55. And then 192.168.1.1, acknowledgement number is 55. We're all caught up. But it took them 300 milliseconds to acknowledge that. Why? Why did 192.168 take 300 plus milliseconds to acknowledge these two small packets coming in? Packet number 13, packet number 14 went out back to back with almost no delay, and 192.168 acknowledged it 300 milliseconds later. Okay, back at the podium. We can edit out the previous few seconds. So the question that I posed was, why did 192.168 take over 300 milliseconds to acknowledge? And I wanted some of you to say, well, there's a Delayed-Ack of 200 milliseconds. Maybe this one's set to 300. No, the answer is, we've already established that the round trip time is about 300 milliseconds. How do we know? From the SYN-ACK of 300 milliseconds. It takes 300 milliseconds for a packet to go to the other side and to come back, which means that these two packets, packet 13 and 14, when they left the station, I'm at 172.16 station. I'm closer to 172.16, and I saw these trains leave my station. And how long does it take for the others to get to the other side? About 150 milliseconds. And how long does it take for the other guy to acknowledge me? About 150 milliseconds, because his acknowledgement has to fly back to me. Okay? So in this case, what kind of operating system is 192.168 running? Windows or Linux? I'm sorry? Windows. Why? Is that a guess or is that an answer? Two small packets, he acknowledged me immediately. Okay? Does that make sense? All right. So we have 8 minutes. I'm going to go back to my sequence number analysis for a second and go over how to do that. And one of the ways I do it is I use profile. I have a thing here called default minimum. I'm going to go to my default, but I'm going to go with no hex view. Okay? So let me zoom in. So you'll notice that I'm a big believer in profiles because oftentimes I don't care about the hex bytes, so I need more real estate. So I have a profile here that says, show me the detail without the data bytes. All right, so I'm going to show you sequence number analysis real quick. Let's look at it from 192 168's perspective. All right, notice I added a column here called sequence number, next expected sequence number, what the acknowledgement number is, and which packet he's acknowledging. Okay? It's a very convenient way to follow the TCP stream. And the way you follow TCP stream is simple. I'm going to give you an analogy, yet another analogy. You're a train station conductor. Your job is to count how many passengers get on the platform. So you have 100 passengers, you collect 100 tickets, you count off 100 passengers. Okay? This analogy is perfect because as TCP, I told you I don't care about packet sizes, right? In a train analogy, as the conductor taking the ticket at the concourse, I don't care what train they get into. They can all pile into the first train. They can all distribute themselves equally among multiple trains. I don't really care. That's not my job. Literally, it's not TCP's job to worry about that. I just give it data to the lower level, which is IP and Ethernet, and they packetize the data. Okay? Not Ethernet, not TCP. So, the way you do sequence number analysis is simple. You have a starting sequence number of 1. This is what's called a relative sequence number, but we'll just go with that for now. And the way the rule works is you take however much data you're sending, TCP length of 124, and you add it to your current sequence number. Okay? So your current sequence number plus the amount of data gives you the next expected sequence number. Which Wireshark, thanks to Guy Harris, a core developer, he said, I'm tired of adding sequence number to this to get the next expected sequence number, so he created a field called next expected sequence number, 125. Okay? It also happens that this is what the other guy acknowledges. So in the TCP train analogy, think of it this way. I sent you 100 passengers. I'm going to start with passenger 101 because I sent you 100. I'm going to start with 101. In this example, I sent you 124 passengers, so I'm going to start with passenger number 125. Passenger number 125 is next to me. I didn't send him yet. The other guy, and then of course the next time you start with one, so this is back-to-back transfer. So I start with 125. I send you 165 more passengers. You add the current sequence number to the amount of data that you're transmitting, and the next expected sequence number is 290. Passenger number 290 is next to me. I'm going to start with passenger number 290. But the other side conductor, as he's counting off passengers coming off the train, he does the same thing. He says, when the first train comes in, he says, oh, okay, the ending part is 125. I expect to start with passenger 125. I expect to receive passenger 125 next. And in the very next packet, sure enough, he receives 125 plus 165 more. So what I do is I notice the next expected passenger is 290, so I send him an acknowledgement for 290. So the acknowledgement coming back is saying, hey, I expect you to start with passenger number 290. Okay? And this is why TCP is reliable. It keeps track of how many passengers it's sending and what passenger I should start with. Okay? So let me start over one more time. And I want you to zoom in on this 2 column here. Sequence number, next expected sequence number. I'm starting with 1. I add 124. My next expected sequence number is 125. I start with 125. I go to 290. I go to 290, and I go to 414. I start from 414. I go to 580. Notice by setting up my Wireshark profile in this way, I can very quickly follow the conversation of 1 to 125, 125 to 290, 290 to 414, 414 to 580. I'm contiguous. I don't even need Wireshark to tell me there was packet loss. Same thing here. I got the acknowledgement column. I know that I had sent it from 1 to 125, 125 to 290. I got an acknowledgement for 290. I'm all caught up. Okay? In addition to that, he's telling me this is an acknowledgement for packet 11. Okay? So if you want to know how to set up these columns, just watch my YouTube page, and because I go into it in great detail. Does that make sense? So this is how we do sequence number analysis. How many passengers have I sent to the concourse, and when do I start? That's my next expected sequence number. Next expected sequence number also happens to be the acknowledgement number that the other guy should be sending. Okay? Any questions so far? Question, yes? Running out of time. Okay, so the question was, in the display filter, there's TCP stream equals 1. Is that doing anything? No, all that's doing is it's identifying how many TCP conversations there are and plucking it out for each. So this is a different socket. So in this particular trace file, if I clear and go to statistics, conversations, there are, oh, just one. Usually it starts with TCP conversation 0. But if you have multiple sockets, multiple connections opening up here, it's just TCP stream equals 1, 2, 3, etc. So there's nothing special going with that TCP streams equals 1. Okay? All right. So it's just a way of identifying which socket you're talking about. All right. So now very quickly, I wanted to go to, now that you guys think you know everything about Nagle Delayed-Ack, this is where the curveball comes in. And let me go back to my all right. So let's follow this through real quick. And I know we're running out of time, so we have a few minutes. So I'll do this very rapid fire. I may have to keep you guys just 1 or 2 minutes. Bear with me, please. So here we have nothing more than syn ACK. Okay. It doesn't even matter for now how close we are to 10 or 192.168. Notice here the 10 dot guy is sending 134 bytes of data, and 192.168 acknowledges 135. Okay. Why did 192.168 1.1 acknowledge immediately? You notice it's 1 millisecond. You'll notice here that I'm starting at 1. Next expected sequence number is 135 because I'm sending 134 bytes of data, and this guy acknowledged 135. Why did he immediately acknowledge when he's supposed to wait for 2 packets? Why is that? So the question is, maybe he had Delayed-Ack turned off. That's one possible answer. It turns out that's kind of difficult to do. So why is it that we talked about the Nagle side, why now this is a Delayed-Ack side. In the interest of time, I'm going to give you the answer. It's called piggyback ACK. It's because the 192.168 had something to send. So if I have something to send, I'm not going to wait my Delayed-Ack timer. I'll just acknowledge you because I'm sending you data anyway. I might as well acknowledge you to where I am. Okay, this is called piggyback. All right, so then the 10 dot guy, because he got the acknowledgement, even though this is 210 bytes, he's free to send. He's free to send because 192.168 acknowledged it without delay because he had something to send. If 192.168 did not have anything to send, we have a deadlock situation. It's only because 192.168 had something to say, he said, I'm going to acknowledge you anyway, which then allowed 10 dot to transmit a small packet, 210 bytes worth. And again, 192.168 immediately acknowledges it because he had something to say, which is fine. And then you get to a point where, look at this. Here's 10 dot, who yet again sent a small packet, 27, because in packet 7, 192.168 acknowledged everything. Okay? He's all caught up, only because he had something to send. Now this time, the 10 dot address guy sent a small packet, but 192.168 doesn't acknowledge immediately. In fact, it takes about 200 milliseconds before he acknowledges it. Why? Because this time, 192.168 had nothing to say. He doesn't have any data that he's going to transmit, so he's kicking back and saying, you know what, I got nothing to say to you. I'm going to wait for another packet to arrive. But the 10 dot guy is over here going, I can't send you this next small packet until you acknowledge my small packet that I just sent to you. So this time the 192.168 says, oh, well, then I got to wait. I'm going to wait till my Delayed-Ack timer goes off, and once that goes off, I'll acknowledge you. Okay? And that's what happened here. Same thing. So once the 10 dot gets the acknowledgement, he sends yet another small packet, and then the 192.168 says, oh, okay, you know what? We're all caught up. I'm going to start sending you these small packets. Here's 16. And then I got full size, full size, full size. So let me ask you a question. This is another case that we talked about. Here's a small packet, 16 bytes. Why is it that he can send another packet immediately after sending a small packet? Because it's full MSS. When it's full, you can go. So even though we have a small packet here in packet number 11, 12, 13, and 14 are full size, and he can go. Okay? Because if it's full, you can go. And then, of course, the 10 dot guy starts acknowledging. And notice which packet he acknowledged. Okay? His acknowledgement number is 1655, which is this guy. Why? Because he waited for this packet to arrive, and then that's when he sent an acknowledgement. When this packet and this packet arrive, that's when he sent an acknowledgement as well. So you can see here where we have 2 packets, acknowledgement, 2 packets, acknowledgement. Does that make sense? Do we go to till 10:30? We have another 10 minutes, right? I was like, oh, there's more here I want to show you, but I'm running out of time. All right, so now I'm going to relax. Let's go back in time and go through this analysis once again. What an idiot. It's what my wife says is absolutely true. Sometimes I'm really good at some things, and then other times, not so much. So let's look at this example now, okay? And to make it easier, I'm going to go back to my default minimum. Default, no hex view. Okay, I'm going to get rid of this hex view, and then... Okay. Why? Because I have the sequence number here, next expected sequence number, and what the acknowledgement number is. So it's easier to follow than looking up here, looking down here, looking up here, and looking down here. So let's take a look here. Okay. I have a sequence number of 4570. Next expected sequence number is 6035. So I sent about 14, you can see it's 1460 bytes. Let's follow this train. 4575 to 6035. 6035 to 7495. 7495 to 8955. 8955 to 9589. But I have a push bit here. So what happened? These 4 packets that you're seeing here is a chunk of data. Okay, let's go back to here. You'll notice that he's sending 1460, no push bit, another 1460, another 1460, and then something smaller with the push bit. So this is a corner case that we talked about earlier, where I have full size, full size, full size, leftover of that bucket. Remember that bucket analogy that I told you about? I got a bucket that I got to send to you, and I start scooping out full scoops worth until I get to the bottom of that bucket, and then there's a little bit left over. Well, this is that little bit left over, 688 bytes or 634, and it comes out to push bit. Okay? This is the end of that bucket. My bucket size happens to be about 4 packets worth. Okay? 1460, 1460, 1460 times 3 plus 634. So let's just out of curiosity do that math. 1460, there's 3 of them, plus 634. 5023. Did I miss some? Let's see. 5323 is kind of an odd number. Okay, there's some more here, right? So let's see. Boom, boom. Okay, so in actuality, it starts from here. It starts from here because I don't see any push bits here, and this is the end of the push bit. So I can actually add here 1, 2, 3, 4, 5, 6. 6 of these full-size packets. So let's see. 1460. There's 6 of them, plus the last had 634 bytes. 93, 94. Okay, that's not even. Sometimes it's interesting because it comes out to be even multiples of 1024. 2048, 4096. So you can kind of see how the application is using chunk size and even multiples of 1024. Okay. All right. So then, so we sent 4 packets. So we have here we have acknowledgement, and this is for acknowledgement for what? Packet number 18. So that's this guy here. Why is it not packet 17? Because it requires 2 packets. So this packet comes in, this packet comes in. He sent an acknowledgement here. This one is packet acknowledging packet number 20 because 19 and 20 come in back to back, and I acknowledge here, packet 20. So this is the packet number, this is the acknowledgement number. Okay. The acknowledgement number will always match up the next expected sequence number. So by looking at these columns, even without this column of acknowledgement for packet 20, 9589 acknowledgement number matches the next expected sequence number of 9589. So just by glancing at this, I know that this is in fact the acknowledgement. Okay. And then I have something else to send. So I start transmit. The 10 dot guy is now transmitting 100 bytes. The next packet, 192.168, immediately acknowledges it, right? So right here, look at this acknowledgement for packet 23 with no delay. But once again, it's the only reason why there's no delay here, even though I sent you a single packet, is because I had something to say. Now you might say, but wait a minute, Han-sang, what about these packets? You sent an acknowledgement here and acknowledgement here. Doesn't that count for anything? The answer is no. Because these are what's called naked acknowledgements, meaning this guy has no TCP level data. Okay? In fact, operating system doesn't even come into play here. TCP stack takes care of this acknowledgement. Okay? And so these two are just naked ACKs. This one's the first time where the 10 dot has something to say. He puts a push bit on it saying, hey, I'm done. This is the only thing I'm going to send you until you acknowledge me. 192.168 again acknowledges immediately, but only because he had something to say. If he didn't have something to say, we would be sitting here waiting again. And 10 dot sends something again, 27 bytes. He acknowledges it immediately because again he had something to say. And this time, yet again, 192.168, because he had nothing to say to the 10 dot at this moment in time, has to sit here and wait. So 10 dot address sent me a tiny packet. I have to wait. I can't acknowledge it. I'm waiting for another packet to show up. But 10 dot is waiting for confirmation before he can continue talking, and therefore there's a deadlock of 200 milliseconds, plus or minus. So what is that deadline here? What is the downside of this Delayed-Ack? Let's look at the summary of this packet trace file. And you'll notice that the duration is about 2 seconds. It's a small example, okay, 2 seconds. Okay? Beginning to end, this entire trace file is 20 seconds. I can also identify that by going to the bottom and, wait, 2.9. Let's see, hold on. So time elapsed, 10 to 13. Oh, look at that. Actually, there's not enough resolution here. It's 2.9, but it's not rounding up to 3. Everybody see that? So in reality, it's 2.9 seconds. When you do the math here, it's like 3 seconds, but elapsed time is 2, so the math is not taking into account the milliseconds. I'll send a note to Gerald, the core developers. I never noticed that before. But then again, I don't often work with 2 second, 3 second traces, so it's a rounding error typically. But this goes back to what Dr. Vince Cerf said, the guy that notices that tiny aberration and investigates. So anyway, it took a 2 second trace to identify. Anyway, 2.9 seconds worth of trace file. If I sort by the delta column, because all the Delayed-Ack penalties are about 200 milliseconds thereabouts, right? So I sort by the delta column, come down to the bottom here, and let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of them, plus or minus. So 14 times 200 milliseconds is 2.8 seconds. So In this example of 2.9 second trace, 2.8 seconds of it was wasted on Delayed-Ack deadlock. This is linear. You extrapolate this to other 1,000 packets, you're going to get similar behavior. Okay? And the reason why you're paying such a horrendous penalty is because both sides start off the conversation with tiny packets, and then every once in a while I send you full-size packets, and then the full-size packet almost invariably ends with a tiny leftover dribble bits that's not a full size, which can kick in the case with delayed acknowledgement. Okay? And so if you're a financial and you're doing online transaction, oftentimes you don't send full packets back and forth, because I'll give you a reason why. When you make a trade with fixed protocol, you say, I want to buy IBM, instrument name is IBM, 1,000 shares for this client at this time. That amounts to about 200 bytes worth of data. Doesn't add up to 1460 bytes worth of data. So you send a tiny order entry, and if the other guy is expecting you to send another packet before he acknowledges, guess what? You're not making another trade for 200 milliseconds. Because I sent you a tiny packet. I want to send you the next trade, but I can't because you haven't acknowledged my 200 byte packet. Yes, question?
So if Nagle is so bad, why keep it to Nagle at all? Why is it
So, okay, so the question is, if the Nagle is so bad in this type of example, why have it enabled by default? Legacy reasons. You can make an argument. Someone said, you know, maybe you can turn off delayed acknowledgement. One time in my career, that's what I had to resort to, turning off delayed acknowledgement to get over this limitation. But it's historical reasons, because these stacks go back a long time, and very few people go back to say, you know what, let's modify the base OS stack. Okay, it stood the test of time, and the application. So the answer is, where do you disable it? Don't disable it at the network card or the protocol level. Have the application developers turn it off with a socket option. So when the application creates a TCP socket, he can say, I want no delay, please, which means turn off Nagle for me. So it's better to have the application turn it off than disabling at the OS level. Having said that, in a modern high-speed network, there's almost no penalty. I don't care if there's 10,000 small packets flying around, and I don't care if there's 10,000 full-size packets flying around, because my bandwidth is adequate. Okay? But the important lesson here is that this trace file, and I want you to go over this Nagle Delayed-Ack, a lot of times people jump to conclusions and say, wait a minute, he must have Nagle turned off because he sent it back to back, and he immediately acknowledged it because Delayed-Ack is turned off. You don't jump to conclusions. This is where fully understand TCP allows you to say, wait a minute, this is called a piggyback acknowledgement. He only acknowledged it because he has something to say. Otherwise, we have delayed acknowledgement. Okay, does that make sense? So I think this was a little bit more rushed than I would have liked. But I actually have a pretty detailed explanation of this online as well on my YouTube page. So if you're kind of like, yeah, I kind of got it, but I don't really get it, either listen to this again or watch my more detailed video online. Question, yes. And the time's up, so for those of you, you're free to go, make it to your next session, but question here? Oh, my book is about baseball. No, it's not baseball. It's packet analysis. So it's a bunch of Sharkfest sessions condensed into a book. So I talk about my approach to troubleshooting. I give you a traffic analysis, packet analysis in the book, what to look for, what to highlight, what the result is, and it's divided up into troubleshooting, different corner cases, and then it ends with data center migration. Okay? All right, thank you very much, folks.